Hi everyone. If you're new here, my name is Ryan and today I'd like to solve this FE exam fluid mechanics problem with you. We're going to walk through the solution step by step, really focusing in on those fundamentals. Before you watch me solve this problem, you can try it for yourself interactively for free using the first link in the description below. It'll take you to a screen just like this where you can have access to all the problems that we've done in our FE exam playlist. You can additionally filter through some of those problems. Let's say you just want to focus in on statics problems. You can focus in on those as well as control the difficulty, input an answer, and it'll give you feedback. If you click view explanation, it'll give you references to the actual manual in these blue bubbles, as well as a video solution, which is a video just like this, except for this particular problem. You can see the answer here would be choice B. So we can move through those problems getting the correct answer, or alternatively, we can flag the questions. So you can try out those problems for yourself, especially this problem. Let's get into this solution. It says an ice cube with a height of 4 centimeters floats upright in a glass of water. If 3 millimeters of the cube is above the water surface, determine the density of ice. Okay, so let's transfer this to a clean sheet of paper. Now, a lot of people never really thought about it, right? Ice is actually less dense than water. That's why we have glaciers floating on top of water. And it has something to do with the hydrogen bonds, but let's not get off the topic here. It says, firstly, an ice cube with a side length. The ice cube side length is 4 centimeters. It's a cube, so all the side lengths, including the depth, are 4 centimeters. They said that ice cube is floating in a glass of water and 3 millimeters of the cube. Now, what we know is that 3 millimeters is the same thing as 0.3 centimeters. So if we kind of draw it out here, that would mean that this kind of height above the surface, this is that 0.3 centimeters. That would mean that this would have to be 4 minus 0.3, which is just equal to 3.7 centimeters. Okay. Now what we need to do is determine the density of the ice. Now, usually when we have a body floating in water, any kind of object, we have to think about Archimedes principle. And Archimedes principle is related to buoyancy. Objects float because they have a buoyant force. And basically what happens is there's the weight of the object, which points down. Additionally, there is the buoyancy force, which is pointing up. And when these forces balance, we have a static equilibrium. Think of static equilibrium. What's the equation for that? We can write the sum of the forces in a particular direction, let's say the vertical y direction, must be equal to 0. What that's telling me is that the buoyancy force is equal to the weight. Now, we know how to compute the weight, right? The weight is just, we can take the density of that object times gravity. Density times gravity is defined as the specific weight. So in order to compute the weight of that ice cube, what we could do is we could take gamma of ice and multiply it by the volume of ice. If you recall, gamma's units are newtons per cubic meter. If we multiply it by a cubic meter, what we would get is the weight. Just to kind of review what that gamma is so that it's not confusing. What we could do is go into the fluid mechanics section, go up to the top near definitions. It'll tell you exactly what gamma is. Gamma is just called the specific weight, and its units are newtons per cubic meter. It represents a weight per unit volume. So if you multiply by the volume, you'll get the weight of the object. Okay, so we understand what gamma is. Additionally, other things are going to come into this problem, like the specific gravity, which is just a ratio of densities or a ratio of specific weights, which are exactly the same. Right? Remember, specific weight is density times gravity. The gravities will cancel out on top and bottom. You can see the definition here. So specific gravity is always relative to water. Something with a specific gravity greater than 1 would be more dense than water. Less than 1 is less dense than water. Okay, so we understood some of those definitions here about the specific weight, and we found the weight of the water. We found the weight of the ice. What about the buoyancy force? Where the buoyancy force comes in is that Archimedes principle basically states that the buoyancy force is equal to the weight of the displaced fluid. Now it's kind of confusing to say it like that, but in our case, if we focus in, the ice is sunken into the water and it displaces a certain amount of fluid. You could see I'm shading in that ice cube. That volume of the fluid has been displaced. What is the fluid that's been displaced? It's water. So we're talking about the specific weight of water multiplied by the volume that was displaced. Well, that's almost equal to the volume of the ice, except this base term is the same, the depth term is the same, but the height is now 3.7, right? So we have that volume of the displaced fluid. Let's see if we can fill in some of these terms. Gamma of ice divided by gamma of water, that's just equal to the specific gravity of ice from those definitions that we were referring to before. Once we have the specific gravity of ice, what we know is that that's equal to the volume of the displaced fluid divided by the volume of that ice cube. Now again, thinking about the volume of the displaced fluid, what we have it is that it's equal to 4 squared. That's this base times the depth times the height. That is this 3.7 centimeters here. And we have the volume of the ice cube. The volume of a cube is just the side length cube. That's 4 cubed. What we can see is that it's just a ratio of 3.7 over 4. The ratio of 3.7 over 4 is equal to 0.925. That's equal to the specific gravity of ice. Now, knowing the specific gravity that we have of ice, it makes sense that it's less than 1 because this object is floating, it's less dense, so that means it would want to float. We also know that the specific gravity represents a ratio of specific weights, or alternatively, it could represent a ratio of densities, like the density of ice divided by the density of water. The density of water is 1,000 kilograms per cubic meter. If you watched a few of those other videos, you know that that's a number that really comes up a lot, so I recommend you go ahead and memorize that value. We can find the density of the ice by just doing that 0.925 and multiplying by the density of water, which is just 1,000 kilograms per cubic meter. That means that the density of the ice is 925 kilograms per cubic meter. Let's go ahead and check that answer here. We have the 925 and we got the solution correct. Let's go ahead and quickly review what we just went over. We said that because the ice was inside of the water, it was floating. We have a static equilibrium situation. We can use Newton's second law. Sum of the forces in the y direction must be equal to 0. We saw that there was 2 forces on that free body diagram. There was the weight, which is just the specific weight of ice multiplied by the volume of this cube. And then additionally, there was the buoyancy force. The buoyancy force is equal to the weight of the displaced fluid. The displaced fluid in this case was water, and its height was different, right? The base and the depth was exactly the same, but the height in this case was 3.7 centimeters. We saw that the specific gravity of that ice term is just 3.7 over 4, which was 0.925. Using the definition of specific gravity, which is the ratio of densities, we were able to compute, knowing the density of water is 1,000 kilograms per cubic meter. We computed that the density of ice is 925 kilograms per cubic meter. And just as a sanity check, that made sense. It should be less dense than water because it's floating. Okay, additionally, the only other choice that we could have chosen, which is less dense than water, was this choice A. So really the choice was just between these A and B term. Additionally, if you didn't remember Archimedes principle, we can go ahead and check inside of the reference manual. You can see I have a page number there, which was on the top, page 180. That's this page right here. You can see Archimedes Principle here. The buoyancy force is equal to the weight of the displaced fluid. If you enjoyed the video thus far, please go ahead and leave a like and subscribe. It really helps out the channel. Thanks for watching. I'll see you in the next video. Bye-bye.